Hey everybody, today we're doing a concavity example. We're looking at the function f of x equals 3x to the fourth minus 4x to the third minus 2. We'd like to know, where is this function concave up? Where is it concave down? Does it have any points of inflection? Big picture, our strategy is going to be to get a second derivative. Concavity is a second derivative issue. We're going to take that second derivative, we're going to figure out where it's positive, where it's negative. Where that second derivative is positive will be concave up, where it's negative will be concave down. Let's see how that goes. So f prime is 12x to the third minus 12x squared. The derivative of the negative 2 goes to 0. The second derivative is the derivative of the derivative. So we just repeat the process. 36x squared minus 24x. Now, as we figure out where this is positive and negative, we want to think in terms of cut points. Where is this going to be 0? Where does it fail to exist? Well, the second question is really easy. It's a polynomial. It's never going to not exist. Domain's all real numbers, not a problem at all. What we need to do is set it equal to 0. When we set a polynomial equal to 0, our primary tool is factoring. And when we start factoring, we always want to take out greatest common factors first. Here, I see a common factor of 12. Pull that out. And I see a common factor of x. I'll pull that out. What am I left with when I divide out 12x from each of these? Here, I have 3x. And here, I just have 2. Okay. Product is equal to 0. That means one of the factors has to be 0. Either 12x is 0, that occurs when x is 0, or 3x minus 2 is equal to 0, which happens when x is 2/3. Those are going to be the cut points when I draw my number line. Notice, by the way, I'm not calling them critical values. Critical value is a phrase that we use for the first derivative. Here, it doesn't quite fit. My number line with my cut points labeled. And let's remember that I'm testing in f double prime. I want to know whether f double prime is positive or negative on each of these intervals. Now, f double prime is here. I'm going to use this form. The factored form will be easier. Why? Just as in the case when we were doing first derivative stuff, increasing, decreasing, etc. When we test values in here, we don't really care whether f double prime is a specific number. We only care about if it's positive or negative. Let me show you what I mean. Let's take x equals -1 on this leftmost interval. I need to plug that in here, but I don't care what value I get out. I just care that I get a negative times another negative. -3 minus 2. And a negative times a negative is a positive. Here, let's test a number between 0 and 2/3. So how about 1/3? When I plug in 1/3, I get a positive times, let's see here, 3 times a third is 1, minus 2 is -1, so it's a positive times a negative. So that's a negative here. And finally, let's check x equals 1 on this far right interval. I get a positive times a positive, which is, of course, a positive. Okay, so when we were doing first derivative stuff, I took these pluses and just indicated the shape of the graph around there by showing an upward sloping line. When I had a minus, I showed a downward sloping line. Here, I want to do something similar, except now I'm talking about concavity. The plus means I have an area of a graph where it's concave up, something like one of those, something like that. Here it's concave down, and here it's concave up. And remember that, of course, a point of inflection is going to be somewhere where the graph changes concavity. We're ready to write our answer. Let's make a little bit of space. So this graph is going to be concave up on the intervals where I have a positive second derivative. So from -infinity to 0, and 2/3 to positive infinity. Make that a little more legible there. Similarly, it's going to be concave down in here between 0 and 2/3. Notice these are open intervals. When we're talking about where a derivative is positive or negative, or whether a second derivative is positive or negative, we always want to use open intervals. We don't want to think about what's happening at these endpoints because, of course, we know the derivative is 0 there. We don't have any particular reason to say it's more positive or more negative there. It's 0. Finally, we can talk about points of inflection. My handwriting gets more slower on the board. So let's just give the x values here. Both at x equals 0 and 2/3, we see that the second derivative is changing sign. Those are both going to correspond to points of inflection. And we're done.